All right, everyone, it's Mr. Rudy back with yet another video. Today, guys, we're going to be talking about our second major topic in equilibrium, which is expressing the equilibrium constant in terms of pressure. So, for a gaseous chemical reaction, the partial pressure of a gas is proportional to its concentration. Therefore, everybody, the equilibrium constant can be expressed in terms of pressure. So if we're looking at the Haber process here, we have 3 hydrogen gas plus 1 nitrogen gas is in equilibrium with 2 ammonia molecules. And we have to write the equilibrium constant in terms of pressure, Kp, and in terms of concentration, Kc. So guys, let's take a look. Let's just dive right into this. So we're going to start with Kc first, since that's what we've been writing since topic 1. So the equilibrium constant is going to be equal to the product. So our concentration of ammonia raised to its stoichiometric power. So there's a 2 in front of ammonia. So there's going to be a 2 here. And then we're going to put that over the reactant. So we're going to have hydrogen gas, H2, raised to the power of 3 times the concentration of N2. Okay. Again, my exponents here, everyone, is just me raising it to the stoichiometric coefficients that are found in the chemical reaction. So 1 for nitrogen, 3 for hydrogen gas, and then, of course, the 2 for ammonia. Now, if we were writing this in terms of our equilibrium constant in terms of Kp, or partial pressures, we're going to say Kp is equal to, ready for this one, the partial pressure of ammonia raised to the second power over the partial pressure of hydrogen raised to the third power times the partial pressure of nitrogen gas raised to the first power. And guys, you'll notice the only thing that I have swapped out here is, of course, that Kp is involving the partial pressures of these gases. Meanwhile, Kc is referring to the concentration of these gases. Okay. Now, one thing I'll say, that the partial pressure of the gas is proportional to its concentration, but as we'll learn in probably the next slide even, that doesn't necessarily mean there are a 1-to-1 value. Okay, so we'll talk about that on the next slide. All right, so how is Kp related to Kc? Well, the partial pressure of a gas does not necessarily have to equal the concentration in molarity, as I just got done stating. Assuming the gas behaves ideally, we can relate Kp to Kc using the ideal gas law and some algebra. So we'll get Kp is equal to Kc times the ideal gas, times RT raised to the delta N power, where R is the ideal gas constant, 0.08206 liter atmospheres per mole per Kelvin. T is obviously the temperature in Kelvin, and then delta N is the sum of the stoichiometric coefficients of the products minus the sum of the coefficients of the reactants. So delta N would be equal to C plus D minus A plus B. Okay, so let's just dive into an example problem here. Nitrogen monoxide is a pollutant in automobile exhaust, is oxidized to form nitrogen dioxide in the atmosphere according to the following chemical equation. So nitrogen monoxide with oxygen is in equilibrium with dinitrogen monoxide. It is given us the value of Kp, which is 2.2 times 10 to the 12th power at not at 12, but at 25 degrees Celsius. And we are asked to find the value of Kc. All right, so let's dive right into this, guys. So we saw on the previous slide that Kp is equal to Kc times the ideal gas constant times T raised to the delta N power. Okay. We want to solve for Kc here, right? We are looking for Kc. So Kc would be equal to Kp over RT raised to delta N. Now the question is well, what's delta N, right? So we got to come up here and we got to find out what delta N is. So delta N is the sum of the stoichiometric products of the products. So there's only one product, and there's a 2 there. So we're going to put 2 minus the sum of the stoichiometric coefficients of the reactants. So we have a 2 from nitrogen monoxide plus, remember, we can put a 1 there from oxygen, plus 1 from oxygen. So delta N is going to be -1. Well, now that we have that information, everyone, I can just go in and start plugging in my numbers into my Kc expression. So we're going to put 2.2 times 10 to the 12th on top here. Then we're going to divide by RT, so 0.08206 times my temperature. Remember, 25 degrees Celsius is 298 Kelvin. You do have to convert temperatures here, folks, so don't forget to. So we're going to put 298 Kelvin on the bottom. And then, guys, we're going to, raise this to our -1 power. And now I'm ready to plug this expression into my calculator. And I got 5.4 times 10 to the positive 13th power. Okay. Now, a quick way that I can check my work, everyone, is if I plug this value back in to Kc, I should get my 2.2 times 10 to the 12th power back out of this calculation. And with that being said, guys, that's our first example problem. Let's move on to the next one. So here we have another one. It says, considering the following equilibrium and corresponding value of K, it says hydrogen gas and iodine gas is in equilibrium with 2HI. The Kc value is 6.2 times 10 to the second at 25 degrees Celsius. I want you to first write the equilibrium expression for both Kc and Kp. Second, interpret the value of Kc. So based on Kc, is the forward reaction favored? Is the reverse reaction favored? Is neither a reaction favored? And then what would happen in terms of what we'd expect to see in the reaction vessel? Would we mostly see reactants or products? Okay. And then finally, what is Kp at this temperature? So go ahead, guys, pause the video and try to solve these things for yourself. All right, everyone, and I hope you were able to get the equilibrium constants for Kc and Kp respectively. So the equilibrium constant for Kc is equal to the concentration of Hi to the second power over the concentration of H2 times the concentration of I2. For Kp, we would write the partial pressure of Hi to the second power over the partial pressure of H2 times the partial pressure of I2. For number 2, interpreting the value of Kc. So Kc is a number that is much greater than 1. So therefore, the forward reaction would be favored. And since the forward reaction is favored, that is letting us know that mostly the products, in this case, Hi, would be in the reaction vessel. And finally, what is the value of Kp at this temperature? Well, Kp would equal 2.2 times 10 to the second because delta N was the 0, and anything to the 0 power is of course just 1. So 2.2 times 10 to the second times 1 is 2.2. So Kp is equal to Kc in this example. Let's move on. So it says, under what conditions below would Kp equal Kc for the following chemical equilibrium? Letter A, when A plus B is equal to C plus D. B, if the reaction is reversible. And then C, if the equilibrium constant is very small. Well, guys, let's just work backwards here. If the equilibrium constant is very small, we know that the reverse reaction would be favored. Okay. So that doesn't make much sense here. So equilibrium constant is small, the reverse reaction is favored. That's really not helping us there. If the reaction is reversible, well, we are referring to an equilibrium here. So it can't be B, that just doesn't make sense. So we finally get into when A plus B equals C plus D, and that is indeed correct. Now, this would be the same case, guys, as if delta n was equal to 0. And as we just saw on the previous example that had numbers involved, when delta n is 0, Kp is equal to Kc. So the way that they're equal, guys, is the sums are equal to each other. Let's move on to our summary slide. So, in summary, the equilibrium constant for gases can be expressed in terms of partial pressures. Kp can be calculated using Kp equals Kc times RT raised to the delta n power. When Kp is equal to Kc, that's when delta n is 0, okay? And Kp and Kc do not have any units because the units will cancel out. And notice, guys, that I have avoided talking about units of the equilibrium pressures thus far. And that's the very reason, is that the units do indeed cancel out. And with that being said, everyone, that's the end of this video. If you have any questions, feel free to shoot me an email.